My name is Christine Thornton, and for my Calculus and Vector CCA, I decided to do it as a giant video. Each unit will get exactly 5 minutes for me to explain the concepts of the unit in its most broken down basic form while doing at least 2 questions as examples. So it'll look something like this time-wise. Each unit 5 minutes, adding up to a total of 35 units, 5 times 7. So I hope I am successful in keeping it to under 5 minutes. If I'm not, you'll hear from me at the end of the video explaining why I had to go over. And enjoy! Starting out strong, we have some definitions. So the derivative, that is the slope of the tangent of the function. It's also like the rate of change, which we've heard of before. And the secant is a line that connects 2 points on the curve, and that's how you get the AROC, so the average rate of change. And then the tangent, which is mentioned with the derivative because they're linked. The tangent is a line that runs in the same direction of the curve but touches it at only 1 point. So as you can see, it's only touching at 1 point, and then it's not touching the rest of the curve. And its slope will give us the IROC at that particular point. So that's the instantaneous rate of change. Okay, so here are some things to know when you're graphing derivatives. So the turning point of the OG function will be the zeros on the graph of the derivative, and then the inflection points of the OG function are the turning points on the graph of the derivative. So for here, these 2 turning points become the 2 zeros, and then this inflection point becomes the new 0. It's not drawn perfectly, and same here, so this turning point becomes the 1, 0, and there's no inflection point, so it's just straight. As you can see, it goes from 3 to 2, quadratic, from quadratic to linear. It's going down a notch. Okay, so our first question is an AROC one, so it's if the hamster moves back and forth where the displacement is given by dt equals 2t cubed plus 4t, where d is measured in meters and t in seconds, determine the AROC of the hamster when t is bigger than 1 but smaller than 2. So to start off, we're going to use that equation and insert 1 in for t to find the velocity at 1. And the answer is 6, and all I did was insert it. So then we're doing the same thing for 2, inserting 2 in for the time. And we get 24. And then last but not least, we're using our equation y2 minus y1 over x2 minus x1. So 24 minus 6 over 2 minus 1 equals 18 meters per second because it's velocity, and that's our average velocity. So the next part of the hamster question asks, determine the IROC when t equals 1 using small centered intervals. And I already have it written out because it's fairly simple, so we're going to plug slightly below 1, 0.99 in to our equation. We get 5.90, and then we're going to plug slightly above 1 into the equation, so 1.01, and we get 6.10, and then same equation, y2 minus y1 over x2 minus x1. Plug all that in, and we get 10 meters per second as the velocity at. So I already know I'm going to run out of time. Just to be clear, I'm not going to do this under 5 minutes. This unit is too big. But here are some basic things we need to know before we jump into a question about limits and finding the derivative using limits. So f1 is f prime. That's just a symbol for the derivative. And then this is the equation we use when finding limits. So so the slope equals limit as h approaches 0, and then f, and then a plus h minus fa, and then over h. And we have to use Pascal's triangle to find when this is squared and stuff, a plus h. It's the best way to find it. So this is x plus y squared, this is x plus y cubed, x plus y 4. I don't know how to say that, but and then we break down each of the steps, which I'll probably have to do in the question. Okay, here goes our first question. I kind of have to write it out on its own and then erase it and then start the question. So it says, if a ball was thrown off a cliff with an initial velocity of 20 meters per second, then its height in meters before it hits the ground is f at x equals negative 5x squared plus 20x plus 40 after x seconds. So part A, determine the derivative, and we're going to use the limit equation. A good way to write out all of this step by step and show you like that. So instead, I'm just going to kind of go through what's here. So we start out by putting the equation we were given into our limit formula. So remember, it's x plus h. So every time we have an x, so it's negative 5x squared, it's going to become negative 5x plus h squared. So then it's plus 20, x plus h plus 40, and then the equation itself over h. And then the next step, we use Pascal's triangle. I don't know why I said it like that. So for that x plus h squared, like I said before, we use Pascal's triangle. So we get this mess, and then everything else kind of stayed the same. This came out of the bracket with the squared. And then moving on, again, there's still a bracket here with a negative 5, so that gets distributed out. And then finally, all this stuff gets condensed into this, still over h. And then we take the h out of the top as much as we can, and then here, cross that h out, and then bam, that's what we're left with. And still we can get rid of that 1h because that's kind of the goal by using the limit as h approaches 0. So 0 is going to go into that h. So we're just going to end up with 10x plus 20 is our derivative. And then there's some like follow-up questions which we can use that derivative. So find the IROC when x equals 3. All we do is plug 3 into our new derivative equation and we get negative 10 meters per second. And then here it asks find when the IROC is at 0. So this time we do the opposite. We put 0 in for our whole f at x thing. And then we sort of got to get rid of everything, move everything to one side. So 2 equals x. So that's when the IROC is at 0. At 2. Okay, here goes the start of Unit 2, polynomials and derivatives. And we have some rules to start off with. So power rule. So here's an example. 3x cubed minus 3x squared plus 2x minus 1. So we can go 3 times 3 is 9. So we take those two. X, this gets knocked down a notch to 2. So negative 3 times 2 is minus 6. X, this gets knocked down to 1, so we don't need to show it. 2 times 1 is 2. This gets knocked down to nothing, and then this one just disappears. So bam, that's our new derivative. And then the product rule is when you're multiplying two things together. So you're going to go the derivative of the first times the second plus the first times the derivative of the second. I don't think I said that right. But here we go. We go through, so the derivative of this is 3 times the second. Derivative of this is 2 times the first. And then you multiply each of these together separately, and then finally you add them together. So 6 plus 6, 12x, negative 21 plus 4, 17. And that's the product. Something I'm very quickly going to note before we move on to the next question is the connection between distance, velocity, acceleration, and derivatives. So the derivative of the distance times time will give you the velocity times time, and the derivative of that will give you acceleration times time. All right, so the first question is, an egg is thrown off a cliff with its height given by h equals negative 5t squared plus 15t plus 24, where t is measured in seconds and h is measured in meters. So first it asks us to determine the velocity and the acceleration at any time t. So that just means we need to find the derivative, because then you can plug any t in. So just do the power rule on this and you'll get the velocity. And then you're going to have to find the second derivative. So that would be finding the derivative of your first derivative, which is velocity. So that's going to end up just being negative 10 meters per second squared because it's acceleration, and bam, it's gravity because it's being thrown off a cliff. The second question it asks us is, what's the velocity at 1 second? So we're going to use that derivative we find, plug in 1, and you get 5 meters per second up because it is positive. Then the next question asks us is determine the max height reached by the ball. So we're going to plug 0 into one side of the velocity, and we get the time of 1.5 because 0 of the velocity is when it's going to be plateaued and at its max height. Then we plug that 1.5 in the time into the original equation, and we get 35.25 meters. So that will be the max height, 35.25 meters. The next question asks us, what is the average velocity for the first 3 seconds? So first we use our velocity equation, we plug 0 in, we get 15. Then we use our velocity equation, we plug 3 in, and we get negative 15. Then we use our y2 minus y1 over x2 minus x1, 15 minus 15, so we end up with 0 meters per second, because that's the average velocity for the first 3 seconds. Okay, so for this next question, I'm dreading it. It's going to make the video longer than it needs to be, but it's important to know this process because we have to use it in multiple units. And it's basically when you're given a function and you have to sketch the derivative accurately, write inflection points, write zeros, that sort of jazz. So for this example, we have y equals 3x to the power of 5 minus 5x cubed. And basically we determine all x-intercepts, we determine all critical points and classify them using the second derivative test, which I'll show. C, determine all inflection points, and then D, sketch the curve. Let's get into it. Okay, so for determining the x-intercepts, we use the original equation and we make it set to equal to 0. So then we take in x to the power of 3 out, and then x to the power of 3 set equal to 0 ends up with x equals 0. And then what's in the brackets set to 0, we end up having to square root it. So we end up with 1.29 or negative 1.29. So those are our x-intercepts. We have 3. To find the critical points, first we find the derivative. And then we set that equal to 0. We take 15x squared out. So then 15x squared just ends up being 0. This ends up being a perfect square, x squared minus 1. So we ended up with x equals 1 and x equals negative 1. So these are our 3 critical points. So this is the table I like to use to kind of sort out how my graph is going to look, what the values that go with my turning points are, so like what the actual points are. So for x being smaller than negative 1, which is our like smallest critical point, we'll use negative 2. Then x equal negative 1, negative 1. I'm just going to come plug these in, then I'll show you guys. 0.5 is between 0 and 1. Then we have 1, and then bigger than 1 is 2. So I kind of went long. And then we plug these numbers that we have, our test values, into our derivative. So I got positive, I got negative for this one, I just got 0, negative for this one, 0, positive for this one. And really all it matters is if it's positive or negative, not the actual values. So then we show it's going up. It's going to plateau at those turning points, going down, plateau, going down some more, plateau, going up. And then we sort of have the shape of the graph, which is kind of useful. And then negative 1, when we plug it into the actual equation, not the derivative, will give us 2. Same with our positive 1 is going to give us negative 2. And then our 0, I kind of figure is the second derivative. But let's do the second derivative test to find our second derivative, which using the power rule, we get 60 x cubed minus 30x. Bam. Then we just plug each of our critical points into that. So we plug 0 in, we get 0. Plug negative 1 in, we get negative 30. We plug 1 in, we get 30. So we know the one that equals 0 is our second derivative. And we also know that if we plug this 0 into the original equation, we're going to get 0. So our inflection point is at 0, 0. To find the other inflection points, or we could even find the 0, 1 using this, we're going to break this down and set this equal to 0, which I didn't even write in, which is embarrassing. So then the 30x is going to be the 0, and then 2x squared minus 1, we break that down. We're going to get the square root of 1/2 and the negative square root of 1/2 as our 2 inflection points, along with the 0. To kind of make this all make more sense, I pulled this up on Desmos instead of actually sketching it, because it's kind of easier to show. So here we go. I clicked on our 3 zeros, which were originally our 3 turning points on the original one, which now became our zeros. But I don't have a sketch of the original one. And we also know that these are our 3 critical points. And so the 0, 0 also ends up being a turning point because it was originally an inflection point, which we found out using the second derivative test. And we also know that we have these 2 other turning points, which this is the square root, the square of the half and the negative square of the half, which we just found out. So they're wacky numbers, but they're down there. So all our values come into play when we draw the graph. This also makes sense because this is quartic 4, and our original one was 5, so it looks right. Okay, on to Unit 3, rational functions and derivatives. Here we have the quotient rule. So it's the second times the derivative of the first minus the first times the derivative of the second over the second squared. So we have all those. We have an example here, 3x to the power 3 plus x over x, and it'll always be like a rational polynomial. So we have all those values here. We plug them on in. These 2 will get multiplied, these 2 will get multiplied, then we subtract them. So we end up with 6x to the power 3 over x squared, which will end up being just 6x. So as long as you follow this rule, it'll all be okay. Another thing to be aware of in this unit is some of the lingo around like limits and such. So this is a continuous function, this is discontinuous, so it's like stops. It has a hole, which is weird. So like, for example, as limit of f at x as x approaches -1 does not equal the limit of f at x as x approaches +1, that means it's not continuous, because they should be the same if it would be continuous. Another example is of a question would be determine the following limit. And then we have a function here, x minus 1 over x squared minus 3x plus 2. So it's quadratic on the bottom, so I did some man. So it's x minus 1, x minus 2. Those x minus 1s cross out. So then it just ends up with 1 over x minus 2. So then we can arrange the bottom, set it equal to 0, and we get x equals 2. So now we know x equals 2 does not exist. Like, that's like the limit. It does not, that does not exist, that value. This question is a doozy. And basically it is asking to sketch this function. And there's a lot of work that has to go into it because it has asymptotes. So we find the x-intercepts just by rearranging the bottom. So it's 1, 0, just chill. We find the vertical asymptotes by factoring the bottom, which we get x and -2. And then we find the horizontal asymptotes because we know the top is smaller than the bottom. So the horizontal asymptote is going to be 0. Okay, so now we have the basis of the graph. We have our asymptotes sort of drawn where they are. And then we can start finding out general placement ideas by using limits. So as x approaches 0 from the negative side, we use limits by using very close to 0, but negative. And we get 50.7, and that's positive. So we know from the negative side, it's going to be positive. So above here. And then we do the same thing, but 0 from the positive side, so we go very close, and we get negative. And that means we know it's from the negative side. And then we do the same thing for the 2 ones. So we go from 2 we go -2 from the negative side. Yeah. And we go slightly more negative than -2. So -2.01. And we get something that's negative. So we know that it's negative. And we do the same thing but positive. We go very close to positive side of -2, and we get something that's positive. So we know it's on that side. And there we have some more general ideas. So now to figure out sort of what's happening horizontally, we go the limit from positive infinity. So that'll be on this side, and we end up with a positive number. So we're going to know this has to cross and go positive. And then the limit from negative infinity, and we go just a very high negative number. We get negatives, that, it goes like that. And we're starting to get a sense here. But we need to figure out like what the value of this is. What the value of this is. Actually, we do know that. We know our x-intercept's at 1. So that makes sense. I should have drawn that from the beginning. But we need to sort of figure out. Basically, what we need to do is figure out this inflection point, because the question asked to be that specific, and this turning point. So turning point, inflection point, we need to find. So to find our critical points, we first need to find our first derivative. And this is our equation, remember? So yeah, we use quotient rule. Forgot the name for a second. It just becomes this big long mess, but you multiply them, then you subtract them. Some things cancel out. And this is kind of as far as you can go. You can't really do anything else at the bottom. You can't really do anything else at the top. So this ends up being your first derivative. Okay, and then to actually find the critical points, we take our first derivative, we set it equal to 0, which you only have to do for the top, because when you're setting it equal to 0, the bottom's just going to cancel out. You gotta do quadratic formula, and we end up with two values. So negative 0.73 and 2.73. Now I know from the graph which we drawn, which I don't have this paper copy, that the negative value makes most sense for the turning point. And then I plug it in to the original function, and I get 1.87. So now I know that negative 0.73, 1.87, that's the turning point. We have the point. Now I'm not 100% sure, because I haven't done the math to figure out which one's the inflection point. I need to do the second derivative test, but I pretty much already figure it's going to be this one, but I am going to go ahead and do the test on both of them. It's a very lengthy process to find the second derivative when you're starting with this. So we start off with quotient rule, and yeah, we have some very long values for like the derivative of the bottom, which ends up getting written out like this. And then we write it all out, and we can get rid of, as you can see, x squared plus 2x. It's a lot, so this can be lowered to 1, this can be lowered to 3. And we can also get rid of it on this side, because you have to be able to get rid of it on both sides to get rid of it on the bottom. So we cross some stuff out, it gets lowered a bit, and then we sort of break it into sections. So this portion on the top that's being multiplied, we're going to bring down here and do, and this portion on the top that's being multiplied, we're going to bring down here and do. So give me one moment. So I went ahead and I found these two multiplied, these two multiplied. As you can see, I put a -1 out front because there's a minus here, and it's easier just to kind of insert that into here now rather than when I put it back into here. It'll just make it simpler, and I'll make it big, one long thing of putting these two together, which I'm going to do in one moment. But there we go, that's that so far. Okay, bam, I put those two different sides together, and then I just had to simplify them. So the x squared went together, the x cubed went together, all that jazz went together on the top until I was finally able to take out a 2 and simplify it to this. I wasn't able to do anything with the bottom. It kind of just had to stay the same. And now I'm going to plug my two critical points in and see what I get. So I went ahead and did it for 2.73, and I got very close to 0, so this is definitely an inflection point. And then this one I got not all close to 0, which we kind of knew. We figured this was our turning point already, and we had already assumed that. So this was a lot of work, but we figured it out. And now I'm going to match my inflection point value. I'm going to plug it in, the 2.73, into the original equation to find what its matching y coordinate is. Yeah, I did that, and the 2.73 matches with 0.13. And we also, I'll rewrite our other values. So the 0.73 matched with 1.87. So that would be our minimum, and it's a turning point. So then I will pull up the graph on Desmos and show you how all this comes together. And here we go. Here's it on Desmos. So we know our one x-intercept at 1 and 0 we found out. Here is our minimum turning point at 0.73 and 1.86. And here's our one inflection point at 2.73 and 0.13. bam! And like our asymptotes are there and we figured it all out and we would be able to sketch it properly. For this unit, which is unit 4, derivative, logs, and exponents, there are a lot more rules, as you can see here. So we start with the chain rule, which I like to use like this version, which is dy over dx will equal dy over du times du over dx. And I'll show some examples of how to use that because they come into play with these ones. I don't remember the name of this rule and I can't seem to find it, but it's using Euler's number to the power of u. And that'll be Euler's number to the power of u. It's not going to change. So like what the function is times the derivative of what it's to the power of u. And then natural log ln. When you have ln u, it'll be the derivative of u over u. And then for logarithmic, it's log b and then u, and it will be the derivative of u divided by just u ln b. I don't really know how to like go into more depth except by showing the rules. And then exponential, which is b to the power of anything, u, and it'll be b to the power of u times the derivative of u, so derivative of what's to the power of 2, times ln b, which is like the base. And then here's some random rules that come into play. So like ln equals 1, ln 1 equals 0, ln e to the power of u equals x, and then e to the power of ln x equals x. So for example, if it asks us to find the derivative of y equals log bracket x to the power of 3 minus 1, so our u is x to the power of 3 minus 1, our u prime is 3x squared, because that's the derivative, and then so the derivative will be 3x squared divided by x3 minus 1 ln 10, because if there's doesn't show you the base of the log, we just assume it's 10. This one has a bit more steps, so it's y equals e to the power of 2x divided by x. So to find f1, we have to do eu for our y over u, and then for our u over x, we have 2, and then we put those together by multiplying them together and inserting back in that 2x. So we get 2e to the power of 2x. It's complicated. I didn't show all the steps, but that's how you do it. So g equals x, and then g1 equals 1. So then we use our quotient rule, we put it all back together, and then you get to this part and it looks kind of funky. But you can just take out an e to the power of 2x because it has on both sides, and then bam, it's been simplified. That's our first derivative. Now we have a question that says, determine the equation of the tangent line to the curve f at x equals negative 2 e to the power of x when x equals ln 2. So we start off by, let's just find out what the matching y coordinate to ln 2 is. So we plug ln 2 into the original equation and we get negative 4. And as you can see here, I didn't actually cross them out. Negative 2e to the power of ln 2, the e and the ln are going to cancel out because whenever they're beside each other like that, they cancel out. And then we are going to plug our ln 2 into the derivative to find the matching y coordinate, like the slope, because we need that to put into our final equation. But it's actually just going to end up being the same equation, the derivative, because it'll be 2eu times 1, and then you put it back in and it's going to end up being the same thing. So we're going to end up with negative 4 again. So then we use y minus y1 equals m times x minus x1, because that's how you find the equation. And then we're going to plug our values in. So we know y1 is negative 4, we know x1 is ln 2, and we know our slope is also negative 4. So we end up with that. And then we can rearrange again. So negative 4 can be moved over to the other side. Our x, I just realized I put 4. Our and it rearranges to this. So we just plugged it in, rearranged, and bam, we have a new equation for that particular part of the curve when x equals ln 2. Okay, so now we're on to Unit 5, exponential and trigonometric derivatives. So sine x, the derivative of that is cos x. And cos x, the derivative of that is negative sine x. You can flip it, so negative cos x will be positive sine x, and you can flip this one as well. And then using trig identities and such, we know that sine x over cos x equals tan x, and that the derivative of that will then be secant squared x is the derivative of tan x. And then cos x over sine x is cot x, and the derivative of that is negative cosecant squared x. Bam. So here's an example. What's the derivative of y equals x squared sine x? So we start using our product rule. Lay them all out. So 2x times sine x will be 2x sine x plus x squared cos x. And you can't really simplify that any further. You kind of just keep it like that. Okay, so now we have a question that sort of goes with Unit 4 and Unit 5, which is like a rate of growth one. So a bacteria culture grows at a rate that is proportional to the amount present. The initial size of the bacteria culture is 100. After 5 hours, there are 600 bacteria. So the question is going to ask us to determine the equation, the number of bacteria after 7 hours, the rate of growth after 7 hours, and when the population will reach 8,000. So I'm going to start by finding the equation. So I do y equals 100 e k5. Use a little k value. And then we plug the 600 in for y. So it's 600 equals 100 ek5. We can divide that 100 out. And then we just have 6 equals ek5. We can put a ln ek5. I'm going to go over here now. And then we can bring the 5k out front just to make things more simple. So 5k ln e. So then a ln e just equals 1. Remember, that was one of our rules. Ln e always equals 1. So we have ln 6 equals 5k. We divide out the 5. And we have k equals ln 6 over 5. Give me a moment and I'll put that back into the equation. Okay, so now we have our final equation. Y equals 100 e to the power of ln 6 divided by 5 t. So we're going to simplify that stuff a bit so we can find it after 7 hours. But first we gotta simplify. So we can get rid of that ln e because remember they can cross out. So then we have 6 to the power of t over 5 when you end up rearranging it. So now we have a new, not a new equation, but an easier equation of y equals 100 to 6 t to the power of 5. We can plug 7 into that t. And we get 1,228.6 bacteria. That's how many there are after 7 hours. Now to find the rate of growth after 7 hours, we gotta find the derivative of this. So we use, I'm pretty sure it's called, the exponential rule to figure out the derivative of just this portion. We kind of just leave the 100 alone. And then we plug the 7 in once we found our derivative. And this is what we get, 440.27. So now to find when the population will reach 8,000, we plug 8,000 in. We can get rid of that 100. So we have 80 equals 6 t to the power of t over 5. You can put a ln in, get rid of some stuff. Ln is always useful for that. Divide out the ln 6. Get 2.45 equals t over 5. You can multiply by 5 to get rid of that 5 on the bottom. It looks really messy right now, but I'm trying to fix it. 12.23 equals t. So yeah, after 12.23 hours, the population will reach 8,000. So we just plugged it in and rearranged and fixed it up. Now we need to find the 57th derivative of sine x plus e to the power of 2x. So first off, we can find the first derivative. So we know it's going to be cos x, opposite of sine x. And then for e to the power of 2x, e to the power of u is 2x, so 2e to the power of 2x. So now let's find the second derivative. So it's going to flip to negative sine x, flip from the cos, that's easy. The derivative of 2e to the power of 2x, multiply them, so it ends up being 4e to the power of 2x. It's just doubled from 2. Instead, we can write it as 2 to the power of 2e to x. And then each time we can do that. So 2 to the power of 3, 2 to the power of 4, 2 to the power of 6, etc., etc., etc. To the power of 5. I skipped 5 for some reason. And that's much simpler and quicker. And then it just becomes a pattern. So we can think, oh, if we're counting 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, this will be the 56th derivative because it's to the power of 4. So then the next one would be the 57th. So we would know that the y power of 57th cos x plus 257 e to the power of 2x. But this would be the 57th derivative because the next one after 56 will be this one in the pattern. And then this would be the 58th derivative, 59th, 60th, etc., etc. And we just put 2 to the power of 57. And there's our answer. Okay, so now on to Unit 6, which is geometric vectors. So here's some things to know, not exactly rules. So scalar is a quantity described by magnitude, like I'm going 30 kilometers per hour. And then vector involves both magnitude and direction. I'm going 30 kilometers per hour south. And then here's cosine law, which is using the sides, and then sine law, which is using angles and sides. So you could find angles and sides. And then equal vectors have the same magnitude and direction, and opposite vectors have the same magnitude and opposite direction, which can also be known as the equilibrium. Okay, and we have even more things to know. So the triangle law of addition, which is tip to tail. So you'll have the A and the B going tip to tail, which I didn't even bother drawing in, but as you can see, tip to tail. And then if the forces acting on an object are added together, the sum is called the resultant force. So this is the resultant vector, resultant force. And then the parallelogram law of addition is tail to tail, so they have the same origin point. So they're going out like that. And then you kind of draw it as a parallelogram. And going straight down, the horizontal center will be the resultant. And then here we have some questions. So state a single vector equal to each of the following. EH plus HF. So we can sort of draw that out. E to H to F. And then this dot 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 will be the vector. And then DC minus BC. DC minus BC, yeah. DC. So B to C, D to C. And since they're subtracting, you kind of go the opposite. So we go our negative B is up here. And then you can draw it like that. It's sort of weird, but you got to go backwards because it's negative. So that will be the negative B to C and D to C. So I'm going to start with a more simple geometric vector, breaking down the X and the Y components of this. So it's 30 degrees. It's going 300 newtons. Poles say it's like pulling a wagon or something. We're breaking down the X and the Y. So for the X, we use cos 30 times 300 because it's cos, so that's the adjacent times the hypotenuse, which is the 30, so it works out. Just drew on my face. And that is going to equal 259.8 newtons. And then for the y, we use sine 30 times 300 because it's the opposite value. And that'll be 150 newtons. And that's our x and our y components of just this one vector. We can figure it out. All right, so now we have a much more complicated question which asks, what is the relative velocity of an airplane traveling at a speed of 735 knots on a heading of east 70 degrees south with respect to an airplane at the same height steering west 50 degrees south at a speed of 300 knots? So I'm going to start drawing that out, and I'm going to have to shimmy some stuff around to get this to work the way I want it to work. So we have both of our values here. So this is 300, this is 735. As you can see, drawn out like that. But we kind of want them to be the parallelogram law, so tail to tail. So I'm going to shift it so the 70 degrees stays where it is. But I'm going to move this 50 up to here. So it's like this, 50 degrees. And this is 735 knots. And then this is 300 knots. And then bam, we have the start of a parallelogram. So give me a moment and I'll make it into a bigger parallelogram. Okay, so I have it drawn out all nice. So then we know that straight across, and that this middle component will be what the relative velocity will be. And we also know we can fill in some blanks here. So 735 will also be across. They're parallel. 300 equal all around, all nice. And we know this angle. So 50 plus 70, why, that's 120. And it will also be across the way. And then just do some subtraction. And we know 60 will be in each of those corners. So we have a lot of info there. And we only need half of it. So we just make a nice little triangle instead of a parallelogram. And we know quite a bit of information about. There we go. We just need one side length. And we can use our cosine law. So I'm just plugging our values into that, which I will show in a moment. Cos 60. See, I plugged them all into the cosine law and I got 640 knots. Now, one moment and I'll show you how to find the angle. So now we use the sine law. So sine theta over 300 and then sine 60 over 640. We rearrange a bit and we get theta equals 24 degrees. And we put that together, so it's 640 knots south, 24 degrees east. And there we go. I'm going to show some more stuff in a minute, but to start off, algebraic vectors are basically similar to geometric vectors but using a coordinate system. So scalar multiplications, you're going to have your coordinate and you can multiply k right into it and distribute, sort of. Vector addition, a1, b1 plus a2, b2. You just add the two a's together to two b's together. A unit vector, you're going to multiply the vector by itself, which would be like the square root of itself. I'll show an example of that later. And then you can find work using force times distance, so kind of slip in some physics in there. And then this is just kind of a note to go with the unit vectors. I will be the I with the little hat will be the x-axis unit vector, j with the little hat is the y-axis unit vector, and k with the little hat is the z-axis unit vector. And I'm about to jump in more of the x, y, z. Okay, so here's sort of how graphing the x, y, z coordinates look like. So you start at the origin, which is 0, 0, 0, and you move along the x-axis. So for this one, our x value is 2, 1, 2, so there. And then parallel to y-axis, which is 3, 1, 2, 3, and then down to there. Yeah, you're gonna go down to where the 3 is, and then up or down the z-axis, so it's -4, so we're gonna go down 1, 2. Okay, so now we're gonna talk a bit more about what this whole system looks like with the x, the y's, and the z's. So we have 2 is our x, 3 is our y, -4 is our z, and we want to plot it. So we're going to start the origin, 0, 0, 0, and we're going to move along the x-axis. So 1, 2. And then we're going to go parallel to the y-axis. So that's 3. So 1, 2, 3. So we're going to go till it's parallel. Bam, that's our point now. And then we're going to move up or down the z-axis. So it's negative, so we're going to move down. 1, 2, 3, 4. So this is our point, 2, 3, -4. And then you'll also kind of be able to create a little triangle with it, which you could use to do more calculations. Okay, here's some even more properties. The commutative property, so u times v equals v times u. Switch them around, fine. Associative property with the k. Eventually it just comes out, kind of like factoring it out, and you end up with u times v. And then the distributive property, where you get to distribute the u in, similar to the way we distribute numbers all the time. And then the cross product of two vectors yields a vector that is perpendicular to both vectors. Therefore, it's only defined in three-dimensional space. And this is the technical equation, but there is a better, more visual way to do it, which I will show later on. Okay, so given u, and we have 3, -1, 5, and v, 2, 4, -1, determine u times v. So we're going to take all the x's and multiply those. So 3 times 2 plus -1 times 4 plus 5 times -1. And then we do the multiplication. And then we add them all together. And we get -3. And that would be u times v equals -3. And now we have a unit vector in the direction of v, and v is 2, 4, -1. So we put the 2, 4, -1 on the top, and then we square root each of the different values on the bottom. Well, we square it and then square root it. So I end up with the square root of 21. And then we end up with each of them separate. So 2 over the square root of 21, 4 over the square root of 21, and -1 over the square root of 21 as our unit vector. Okay, and now we have a more complicated question, which is determine the area of the triangle with vertices of P, which is 3, -1, 7, Q, which is -2, 5, and 4, and R, which is 1, 8, and -2. So I go ahead and I draw that out. I draw it as a parallelogram. P, Q, R. So then I want to find PQ, so I'm going to subtract Q from P, which I do down here, and get these 3 sets of coordinates. And then I want to find P to R, so I subtract R minus P, and I get these coordinates. And then I got to multiply the 2 new sets I have together. This is because we are finding area, which is base times height, which we'll later divide by 2. So we just found P to R and P to Q, so the base and the height. So now we just need to multiply them together. And this is where we use cross multiplication. So we figure this is I, this is J, this is K. I, J, K on each of those. Then we put PQ here, we put PR here, and we line them up in order. IJK, IJK, which I'll show. Just give me a moment. K, so -3, -9. I, -5, -2. J, 6, 9. K, -3, -9. And we have them all set up in a row. IJK, IJK. Now, we're going to cross them. Now, for this cross multiplication trick. Cross product, actually. So we cross off the ends. They just get written off. And then cross, 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 cross. So we take that 6 times the -9, which we crossed, minus the 9 times the -3. So they made an X. So that's why they're getting subtracted from each other. So then, next pair, the -3 and the -2 minus the -9 and the -5. Running out of room, so I gotta go down below. The -5 and the 9 minus the -2 and the 6. And then we do that multiplication with each of them. So we end up with -54 minus 27 so they each have been multiplied. Now they just need to be subtracted. So -27, -39, and -33 is our new set of values. So that will be the area of the whole parallelogram. So we just need to divide it by 2 and into its proper units. So to finish it off, I was putting it into its unit vectors form, so squaring each one and then square root, which I did, and then had to divide it by 2, so we ended up with square root of 3,339 divided by 2 units squared is the area of that triangle. So that's all of calculus and vectors for my portfolio. I definitely did not do it under 5 minutes for each unit. It's definitely long, but I think it had to be long in order for me to properly cover everything in a way that would be useful for me to be able to look back, revise on, and review for calculus and vectors in the future. Thank you for watching, and that's all.